Hello everyone. Today we will talk about a new topic that is biomolecules. So, what are biomolecules? These are the organic compounds present as essential constituents of living organisms in different cells. Now, the major biomolecules are carbs, means carbohydrates, proteins, fats, vitamins, and of course DNA. So today we will talk about carbohydrates. So what are carbohydrates? Carbohydrates, as the name suggests, hydrates of carbon. So carbohydrates are naturally occurring organic compounds which are hydrates of carbon. For example, glucose C6H12O6 can be represented as C6H2O whole 6 times, while sucrose is C12H22O11, but it can be represented as C12H2O whole 11. That means carbohydrates are hydrates of carbon. But if this definition is true, then there are many compounds which are not considered as carbohydrates but they satisfy this definition. For example, formaldehyde, CH2O, so it's a hydrate of carbon. Acetic acid, C2H2O whole twice, means CH3COOH can be written as C2H4O2, so C2H2O whole twice H2O. So these molecules, they fit into the definition of carbohydrate but are not considered as carbohydrates. Now similarly, there are some compounds like ribose, C6H12O5, deoxyribose, C5H10O4. These are carbohydrates but these are not the hydrates of carbon. So that means we need to modify the definition of carbohydrates. So what are carbohydrates? Carbohydrates may be defined as optically active polyhydroxy aldehydes or ketones, or the compounds which produce such units on hydrolysis. So they are optically active molecules, optically active polyhydroxy aldehyde or ketones. Now, according to the above definition of hydrate of carbon, which of these molecules are not able to satisfy, they satisfy the definition but they are not considered as the carbohydrates. So out of glucose, acetic acid and ribose, the answer is glucose and acetic acid. They satisfy the definition but they are not considered as carbohydrates. Now next is the classification of carbohydrates. Now carbohydrates may be classified as simple or complex carbohydrates. Simple carbohydrates, they may be monosaccharides or disaccharides, but complex carbohydrates are simply the polysaccharides. This is the classification of carbohydrate on the basis of their hydrolysis products. Means on hydrolysis, how many units they will be generating. So let us talk about monosaccharides. These are the simplest carbohydrates, cannot be further hydrolyzed. For example, glucose, fructose, galactose. So what are oligosaccharides? Oligo means few. So these carbohydrates on hydrolyzing gives 2 to 10 molecules of monosaccharides. So depending upon the number of molecules of monosaccharides, they can be classified as disaccharides, trisaccharides, tetrasaccharides. But mind it, the total number of the units can be 2 to 10, means 2 to 10 monosaccharides. For example, maltose, lactose, sucrose. Coming to the third is the polysaccharide, means carbohydrates which give a large number of monosaccharides on hydrolysis. They are called polysaccharides. For example, starch, glycogen, fibers, cellulose, etc. Now we can also classify the carbohydrates on the basis of their sweetness. means whether they are sweeter in taste or they are not sweeter in taste. So based on taste, they can be classified as sugars or non-sugars. So sugars means they are sweeter, non-sugars means they are not sweeter. So all oligosaccharides and the monosaccharides are sugars, whereas polysaccharides are non-sugar. Next is based on the nature. So we can classify on the basis of nature also. How? We can classify as reducing sugars or non-reducing sugars. So what are reducing sugars? The sugars which reduces Fehling solution, Tollens reagent or Benedict's reagent. They are called reducing sugars. Means they must have free aldehyde group. For example, glucose and galactose. Number 2 is non-reducing sugar. Means these sugars will not be able to reduce the Tollens reagent or Fehling's solution. For example, sucrose is a non-reducing sugar. Non-reducing sugar. Now, let us talk about different types of monosaccharides. So, I told monosaccharides may be defined as the simple carbohydrates which cannot be hydrolyzed into still simpler compounds. Now, in these monosaccharides, there may be the aldehyde group or there may be the ketone group. So, monosaccharides which contain an aldehyde are called aldoses, whereas which contain ketone are called ketoses. Now, these aldehyde molecules may have 3 carbon, and they are called as aldotriose. For example, glyceraldehyde. If there are 4 carbon, we call it as tetrose and aldotetrose. Example is erythrose. If there are 5 carbon, means aldopentose. Example is ribose. If there are 6 hexose or aldohexose, example is glucose. Similarly, in case of ketones, we can say ketotriose, ketotetrose, ketopentose. Ketotriose, example is dihydroxyacetone. Ketotetrose, example is erythrulose. Ketopentose, example is ribulose or xylulose. Next is, let's talk about the first monosaccharide, which is glucose. The another name of glucose is dextrose, commonly called grape sugar. Formula C6H12O6. Now this sugar is present in our body, in our blood. So it is also called blood sugar. So how to synthesize, how to manufacture? So it is manufactured from sucrose as well as from starch. So number 1 is from sucrose. The hydrolysis of sucrose in the presence of acid gives glucose and fructose. Equimolar mixture of glucose and fructose. Whereas when we prepare it from starch or cellulose, then on hydrolysis at 393 Kelvin, 2 to 3 atmospheric pressure, it gives glucose. Now glucose in our body gets stored as glycogen. Let us now talk about the structure of glucose. Now glucose has got 6 carbon atoms, 1 aldehyde group, and there is 1 primary hydroxyl group and 4 secondary hydroxyl groups. But how to illustrate all these things? Now it can be illustrated by the different chemical reactions. Different reactions are, number 1, when glucose reacts with HI, it gives normal hexane. When glucose reacts with HI, then on heating, it gives normal hexane. Now this normal hexane molecule shows that there are 6 carbon atoms. Now this reaction takes place in the presence of red phosphorus, and on prolonged heating it produces normal hexane, showing that there are 6 carbon atoms in glucose and they are in a straight chain. Glucose on acetylation with acetic anhydride gives a pentaacetate glucose. It confirms the presence of 5 hydroxyl groups because hydroxyl group undergo acetylation to form pentaacetyl glucose. Next is glucose reacts with hydroxylamine to form oxime, and it reacts with hydrogen cyanide to form cyanohydrine. Now these reactions simply confirm the presence of carbonyl group in the glucose. Glucose reduces ammonical silver nitrate solution, means Tollens reagent test. It reduces Tollens reaction or Tollens reagent to the metallic silver, and also Fehling solution or Benedict solution to reddish brown cuprous oxide, and itself it gets oxidized to gluconic acid. Now this reaction confirms the presence of aldehyde group because ketones cannot reduce Tollens reagent. Now with mild oxidizing agent like bromine water, glucose is oxidized to gluconic acid, and glucose on oxidation with nitric acid gives saccharic acid. So first reaction shows the formation of gluconic acid on adding bromine water, and in the presence of strong oxidizing agent it gets converted into the saccharic acid. Glucose on reaction with methyl alcohol in the presence of dry HCl forms alpha and beta methyl glycosides. Now the reaction occurs only at the OH of hemiacetylic carbon. So this is first structure is representing open chain structure of glucose, whereas the other two structures here are representing hemiacetal structure of glucose. Now these reactions simply show that in the open chain structure of glucose there are 6 carbon in one chain. There is one aldehyde group. There are 5 hydroxyl groups. Out of those 5 hydroxyl groups, 4 are secondary hydroxyl and 1 is the primary hydroxyl group. Now there are some reactions which are not explained by the open chain structure of glucose. So these reactions can be only explained if we consider the cyclic structure of glucose. What are those reactions? Number 1, glucose does not give 2,4-DNP test, Schiff's test, and does not form hydrogen sulfide product with sodium bisulfite. Number 2, the pentaacetate of glucose does not react with hydroxylamine, indicating the absence of free aldehydic group. Number 3, glucose exists in 2 different crystalline forms, alpha and beta forms. These are called anomers. They differ in optical rotation. They also differ in their melting point. So on the basis of these reactions which were not explained by the open chain structure of glucose, it was implied that glucose possesses the closed structure. So let us now talk about the closed structure of glucose. Closed structure of glucose means the cyclic structure of glucose. The cyclic structure of glucose can be represented in the form of pyranose ring structure. Pyranose ring structure means its structure is similar to the pyrene molecule. Now that pyrene can be represented by 2 forms, by 2 ways, alpha as well as beta form. So alpha form and beta form of glucose. These are called the anomers. Alpha and beta forms of glucose are called anomers. So what are anomers? Anomers are isomers which have a different configuration across carbon atom number 1, means the first chiral carbon atom. So what are anomers? These are the isomers which have different configuration across the first carbon atom of the molecule, means across the first chiral center of the molecule. There are two anomers possible, alpha and beta glucose forms. Now in the alpha and beta form, in the alpha form, at the first carbon atom, OH group is on the right hand side, whereas in the beta form, OH will be on the left hand side. So glucose having first configuration mentioned here, that is at C1 the OH group is on the right hand side, is called alpha form of the glucose, whereas when it is on the left hand side it is called the beta form of the glucose. Both of these forms are optically active, means they can rotate the plane polarized light. Both of these forms, they differ with respect to specific rotation. Alpha form has got plus 1.5 degrees of specific rotation, and beta form has 19.5 plus 19.5 of specific rotation. Now look at the open chain structure of glucose. It is at the center, open chain structure of glucose. Now what happens? This open chain structure will form hemiacetal form. How? The OH from the fifth carbon will add on the first carbon of the glucose molecule. As a result, the structure gets closed, and that closed structure represents the hemiacetal form of glucose. So there are two hemiacetal forms possible, alpha as well as beta form. And in the closed chain structure, closed ring structure, it can be represented in the form of pyrene, means pyranose ring structure. Now remember, in order to draw the structure, all the atoms or the group of atoms which are on the right hand side, they are represented downwards, and which are on the left hand side, they are represented upward. Look at the alpha D form. At the first carbon, hydrogen is at the left side, means we have to show it upward. OH is on the right side, so we have to show it downward. Similarly at carbon number 2, H is again on left and OH is again on right. At carbon 3, OH is on the left, so OH and H is on the right, so OH will go upward and H will come downward. So these are the two anomers of glucose, alpha D form and beta D form. Now what is the meaning of capital D here? Capital D. Capital D simply represent the relative configuration. Relative configuration. Capital D. It is not text store. It simply represents the relative configuration. Now the exact configuration of glucose has been established by Fischer on the basis of its chemical characteristics. And also some other structural investigations have been correctly named as the D-glucose. So what is this D? What does it refer? Capital D refers to D-glyceraldehyde. D-glyceraldehyde means glyceraldehyde molecule in which OH group is on the right side is called D-glyceraldehyde. So D-glyceraldehyde molecule. Look at here D and L notations. Glyceraldehyde molecule, D-glyceraldehyde. Here OH is on the right hand side. Look at the glucose, the last second carbon atom of glucose. OH is on the right hand side, so it refers to D-glucose. Look at L-glucose. Here OH is on the left hand side, so that's why its configuration is L. So D-glucose and L-glucose.